Hello students, welcome back to the classroom point. In our today's class, we shall discuss the chemical kinetics introduction part along with the rate and rate of reaction. So let's begin the class now. Chemical kinetics. So basically chemical kinetics deals with the speed of the reactions. So which reaction goes faster and which reaction goes slower. So this comparison usually we get in the chemical kinetics lesson. So in the chemical kinetics, before going to the details of the speed of the reactions or the rate of the reaction, let's try to know actually how many types of reactions are there and to which reaction this chemical kinetics can be applied. So based on the speed of the reaction that is going to occur, the reactions are basically classified into three categories. They are very fast reactions, so that first one is very fast reactions. Let us see what are the very fast reactions. So these reactions do not give sufficient time to find their speed. So these reactions occurs instantaneously. Immediately the reactions takes place and we cannot identify what is the speed of the reaction that they are going to takes place. So they takes place immediately the moment you add the reactant molecules. So let us take some examples. Examples are strong acid base reactions. Example, if you take NaOH plus HCl, the reaction takes place immediately to give the NaCl and the water. Similarly, if you take precipitation reactions, example, when you take AgNO3, add some NaCl, the moment when you add both of these compounds, immediately you get the white precipitate of HCl along with NaNO3 molecule. And similarly, nuclear reactions. Nuclear reactions, or you can take the explosive reactions. So these reactions takes place immediately so that someone cannot sit there to calculate their speed. So that these are called as the very fast reactions. Chemical kinetics cannot be applied here because to measure these reactions we need sophisticated equipment, which is difficult also. And second one is very slow reactions. These are exactly opposite to the very fast reactions. These very slow reactions need too much of time to complete the reaction. Example, rusting of iron, in the presence of oxygen and moisture. So which takes a lot of time so that we cannot again wait to calculate its speed. Similarly, reaction between H2 and O2 in the absence of catalyst. So this reaction goes very slowly in the absence of catalyst. So that's why it is called as again very slow reaction. Remember that If catalyst is not used, this reaction almost do not occur. When catalyst is used, the reaction occurs. If the reaction is called as the very fast reaction, then we should not get any oxygen and hydrogen in the nature. That means still oxygen and hydrogen available means they are not reacting with each other without a catalyst. And the third one is reaction between N2 and O2 in the absence of light. Example, N2 plus O2 to occur as to produce 2NO, it needs light, or else you need the approximately 1470 kelvins to the 2200 kelvins of the temperature. So usually this reaction occurs during the lightning. So that lightning can produce the more amount of the energy. So that energy helps in breaking of the bonds, triple bond between the nitrogen as well as the double bond between the oxygen molecule, so that finally NO molecule is going to produce. So all these reactions takes place with a slower rate, and someone needs to sit there to calculate their speed cannot be possible. That's why chemical kinetics concept is not applicable to the both very fast reactions as well as the very slow reactions. Third one, reactions that takes place with moderate speed. So for these reactions we can apply the chemical kinetics, because in these reactions they go with moderate speed. The reason for this moderate speed is breaking of the old bonds, and formation of the new bonds. Formation of new bonds takes some time. That's why we can calculate the speed of these reactions. That means these reactions which takes place with moderate speed, usually covalent reactions, means the reactant molecules must have the covalent bonds. And in these cases, these are almost all ionic reactions. So ionic reactions means breakage of the bonds and the formation of the bonds are not present. Only ions gets rearranged. That's why immediately the reactions takes place. That's why they are called very fast reaction. These are very slow reactions. These cannot be applied the chemical kinetics. But these reactions as covalent bonds are involving, so breaking of the old bonds and the formation of the new bonds takes some time, so that we can get the sufficient time to calculate their speed. So our chemical kinetics concept is applicable to the reactions that are going to take place with the moderate speed. Now let us take an example for this is inversion of cane sugar, or else you can call it as a acid hydrolysis of the cane sugar. You see that here C12, H22, O11, when you add water molecule in the presence of the acid catalyst like H2SO4 or HCl, so the sucrose molecule dissociates into glucose and fructose molecules. That takes some time. So we get the glucose and fructose. And second example here is esterification reaction. Esterification means reaction of the carboxylic acid with alcohol in the presence of acid catalyst to produce ester plus water molecule. So this reaction also takes some time, so that we can apply the concept of chemical kinetics to this reactions takes place with the moderate speed. Now let us try to see the basic things in the chemical kinetics, that is rate and rate of reaction, and how to calculate this both rate and rate of reaction. Rate. So rate usually called as the speed also. But we don't use the word speed in chemistry, but we are using the word rate. Rate is not the cost or price. It is just like a speed. Then why are we not using the speed or velocity to measure the speed of the reactions? Very simple thing that in case of the both speed and velocity, there is a physical difference is there in the object distance. For example, a particle is moving with a certain velocity. That means the particle is moving from one place to the another place in a particular given time. That we are calling it as a velocity. It means there is a displacement of the particle. So in the case of the smaller particles, during their displacement, we use the word velocity. And for the larger object like bus is moving, so bus we don't call it as a velocity, we call it as a speed. So for larger objects we are using the another terminology, that is a speed. So when bus is moving from one place to the another place with a particular within the given duration of the time, that we call it as a speed. So for larger objects we are using one type of terminology and smaller particles another type of terminology to calculate their displacements. So one is speed, second one is the velocity respectively. But in the case of the chemical reactions, chemicals don't move from one place to the another place. The reactions happening within the given test tube or the beaker, whatever it may be. But there is some change. That change is not in the form of the displacement or the moving from one place to the another place, but in the form of the concentration. So that change which is taken place within this particular area, that is called the rate. So when you are using the word rate, that means actually movement of the displacement is not there, but a change is observed. So that change when you are applying to the chemical reactions, that is what called the rate. So but if the reaction takes place, that change, whatever the reaction change is there, so the change whichever is taking place in the reaction, if it takes place with a faster rate, that is called the higher rate. If it is going slower, that is called the slower rate. So faster speed means higher rate, slower one means it is called the slower rate. So now let us see here rate definition. The change in either concentration or pressure of either reactants or products in the given time duration is called rate. So here the change in the concentration or in the presence of the pressure. For gaseous reactions we use the terminology pressure, or else we can use the concentration. So this change can be observed using the either reactants or using the products. So change with respect to reactants or change with respect to the products in their concentration or pressures is called the rate. Remember that rate is always positive. Change is always positive. Negative changes does not occur. So if reactants are converting into the products, means some change is there. That change is always equals to positive. So change never be negative. So let us take a reaction here. Example, in a reaction, reactants convert into the products. In any particular reaction, reactants when converting into the products, starting reactant molecules concentration shall be very high. But when time passes, reactants start converting into the products. That means concentration of the products increases. Concentration of the reactants gradually decreases. That means products appears in a reaction, reactants disappears in a reaction, or else we can call products accumulated in the reaction and concentration of the reactants gradually decrease. So this rate can be written in the form of rate is equals to difference in the concentration of the reactants in a given time, difference in the time, Or else we can write down with respect to the products, difference in the concentration of the products divided by difference in the time. That means time duration. But in any particular reaction, concentration of reactants decreases, so that we show in the form of the negative sign, and concentration of the products increases, that is shown in the form of the positive sign. But you may ask the question, as I said just now, the rate is always positive. Then here, whenever you are calculating, if you get the negative value, that value, entire value has to be multiplied using the -1 to get the positive rate. So rate is always positive. So here rate can be written as now, rate is equals to difference in concentration, means higher concentration minus lower concentration divided by higher time minus lower time. Or else in terms of the pressure, higher pressure minus lower pressure divided by higher time minus the lower time, because rate is always positive. That's why we have to take the higher values starting and lower values later. So basically we can write down the rate as rate equals to difference in the concentration by difference in the time. So here concentration units are molarity, time units are time you can take here, or else seconds you can take, molarity per time. So here you can take another one in terms of the pressure, it equals to difference in the pressure divided by dt is equals to pressure units are atmospheres or the bars, you can take atmosphere per time. So these are the units of both rate in terms of the concentration and rate in terms of the pressure. Now let us take the another equation. If reactant is given like this, reaction is given like this, even though the rate of disappearance of the reactant of R, we have to write down as minus d into concentration of R by dt, and rate of appearance of product can be written as plus d into concentration of the product by dt. That means these stoichiometric coefficients we are not including in the representation of the rate with respect to a particular reactant, because whatever the stoichiometric coefficients in the balanced equation it may be, when you are using the rate basically deals with only change in the concentration, but number of stoichiometric coefficients are not involved. So that particular reactant or product concentration changes or pressure changes, that change only we calculate, but we don't take the number of stoichiometric coefficients. That stoichiometric coefficients only simply says that the concentration. So concentration changes. That concentration change already we have taken in the form of this numerator value square bracket. So change in concentration by change in the time. Let us see average rate. Rate average. So when the rate is calculated over a period of the time, then it is called the average rate. So let us take a particular graph here. I am taking the concentration and here time, concentration of reactants let us take here. Concentration of the reactants gradually decreases in a particular reaction. So imagine the concentration of reactants are moving like this. So whenever you are using the average rate, so whenever you take the average rate, here we are mentioning the over a period of the time. Let us take here 2 points in the graph. So this is the change in concentration, that gives delta C, and this is the difference of the time, this gives the delta T. So for this, rate average is taken as delta C by delta T. So whenever the term delta is used, that means it is for the larger duration of the time. But nowadays we can use both differentiation as well as the delta terminology, so that much difference we are not observing, because the both meaning is higher concentration, change in the concentration by change in the time. Here also change in concentration by change in the time, so that you can write down this one as a D into concentration of the reactant by difference of the time. Now in terms of the products, so that concentration of products with the time gradually increases. So for this one, you find out the change in concentration here. So let us take this concentration, and this is the concentration change. So this is the change in the concentration of the products, and here in this time duration delta T is taken, so that now average rate for these products can be written as plus delta P by delta T, or else you can write down the plus D into concentration of product by difference of the time. Here reactants we are mentioning, so that we have to take the negative sign, there we are taking the positive sign. Next, let us take the instantaneous rate. Or instantaneous. The difference between the instantaneous rate and average rate is, for the average rate you need the large duration of the time. So in the large duration of the time means you have started the reaction, after some time if you find the rate of the reaction rate, then that is called the average rate. Instantaneous time means not the duration. At any given moment of the time, what is the speed of the reaction? That is called the instantaneous reaction. The difference between the average rate and instantaneous, one more thing here is, in a particular reaction, usually the concentration of reactants gradually decreases, concentration of the products gradually increases. So starting time rate will be high for the reaction. When the concentration of the reactants gradually decreases, automatically speed of the reaction also gradually decreases. Then in such cases, for the average, when you are calculating the average rate, you will get the only average value, but not exactly at a given moment. Means starting value may be higher and later value may be slower. So that average value we are calculating for the rate of the reaction, that is for the average rate. In the case of the instantaneous rate, starting you can calculate, even after some time also you can calculate, but at any given time when you are calculating the rate, that is called the instantaneous rate. Means at that particular moment we are calculating the rate. So for instantaneous rate, dt or delta t approximately is equals to 0. Means change of time is not observed, because you are calculating at a given moment of the time. So let us take the equation here. See the concentration of reactants I am taking here and time. So concentration of the reactants gradually decreases. Imagine these are the time periods, 0 seconds, 100 seconds, 200 seconds, 300 seconds and 400 seconds and 500 seconds and like this. So I want the rate exactly at the 200 seconds. So that 200 second we have to mark it. So after marking that, exactly you have to draw a particular tangent that touches the graph exactly at the 200 second. So exactly touches this curve at the 200 second, and from that you have to get this line. If you want to calculate the rate at the 200 second, so you have to draw a tangent on the curve that touches the curve exactly at the 200 second. Then what could be the length of this line? The length of the line could be anything. You can take the shorter length, you can take the larger one. So here, if you take this one, now here you are calculating this is a change in concentration, and this will be the change in the time. So these values, rate instantaneous for the reactants minus delta C by delta T, or else minus D into concentration of reactant by difference in the time. This is a difference in the time. You can take these two values. higher value minus lower value, so that you will get exactly the time period you are calculating here. If you take the shorter value, then the distance value also gradually decreases. Or else you can take exactly the 200 second if you calculate the concentration change. But concentration change exactly at the 200 second cannot be calculated. That's why we draw a line that touches the curve exactly at the 200 second, so that the line length could be anything. If the line length increase, both the concentration, both the time also increase. If the line length decrease, concentration and time duration also decrease. That gives the change of the concentration of the reactant exactly at the 200 second. That is called the instantaneous rate. So this is at the moment, this is over the period of the time. Next one, relation between rate with respect to concentration and rate with respect to pressure. So we can take the concentration as well as the pressure also. So we know that ideal gas equation PV equals to nRT, and P by RT is equals to N by V. We can rearrange this equation where concentration equals to number of moles per volume of the compound. So that here in the place of N by V, I can write down this C. So now let us take we know that one more equation, that difference in the concentration divided by difference in the time, that is what called the rate representation. So in the place of difference in concentration, where this is representing the concentration, I can write down the P by RT, so that I can write down the difference in the pressure divided by difference in the time into 1 by RT. This is the relation between the difference in the concentration with the difference in the pressure for a given particular reaction. Rate of reaction. There is a little difference between the rate and rate of the reaction. In the case of the rate, we are just writing the rate equation, means rate representation only with respect to a single compound. That means we take the reactant molecules or the product molecules. So change in the concentration of that reactant molecule or product molecule when represented, that is called as the rate. But rate of reaction means in a particular reaction there may be many reactant molecules as well as many product molecules. When you are relating the change of the concentration of one reactant molecule with another reactant molecule, or one reactant molecule with one product molecule, or a product molecule with another product molecule, means you are relating. When you are getting the relation between the difference in the concentration of the either reactants or products which are participating in the entire reaction, you are relating all these molecules, that is called the rate of reaction. So in the case of the rate of reaction, we need to consider the stoichiometry coefficients. For a rate, we don't consider the stoichiometry coefficients, because the rate is always with respect to single compound. But a rate of reaction means in that reaction, whatever the number of reactant and product molecules are involved. So we are comparing the speed of appearance and disappearance of the reactant molecules as well as the product molecules. That's why we need the stoichiometry coefficients. So let us take an example here. H2 plus half O2 gives rise H2. So in this reaction, H2 molecule, for every hydrogen molecule disappears, only half the oxygen molecule disappears and one H2O molecule appears. Means the speed of the H2 molecule disappears is twice the speed of the oxygen molecule, or else the speed of the oxygen molecule disappears is half of the disappearance of the hydrogen. Why? Because for every one hydrogen molecule, only one oxygen molecule is going to participate in the reaction. That means when you are relating the one reactant molecule with another reactant molecules, which is playing the major role, stoichiometry coefficients. So when you are relating in a particular equation, means when the rate is applied to the every reactant molecule in the equation, and when you are relating them, then we must consider the stoichiometry coefficients. So let's take the general equation. Reactant gives products. Here no stoichiometry coefficients are there. So rate of reaction is equals to minus d into concentration of R by dt is equals to plus d into concentration of product by dt. Means if for every one reactant molecule consumes, one product molecule appears. That means both rates are same. Next, let us take A, R giving the products P. Now, rate is equals to minus 1 by A d into concentration of R divided by dt is equals to plus d into concentration of P by dt. So, this rate, if divided by the stoichiometric coefficient, that gives the rate of a reaction. So, let us take another one. A gives small b and b. For this reaction, rate is equals to minus 1 by A d into concentration of A by dt is equals to plus 1 by B d into concentration of B by dt. So, in the rate of reaction, the rate with respect to every compound is equals to the rate with respect to the other compound, provided that the stoichiometric coefficients are used 1 by stoichiometric coefficient. That means their rates are divided by their stoichiometric coefficients. So, here rate of reaction with respect to A is written as minus 1 by A d into concentration of A by dt. But rate with respect to A is equals to minus d into concentration of A by dt. This rate also known as the rate of disappearance. Rate of disappearance of A is equals to minus d into concentration of A by dt. So, in the place of this one, we can write down that rate of reaction is equals to minus d into concentration minus 1 by A d into concentration of A by dt. This is what rate of reaction. In this, rate is equals to minus d into concentration of A by dt. So, we can relate the rate of disappearance of A with the rate of reaction as, so here rate of disappearance of A is equals to, we know that minus d into concentration of A by dt. But rate of reaction means 1 by A minus 1 by A d into concentration of A by dt is there. So, if this A you send this side, then it becomes A into rate of reaction is equals to minus d into concentration of A by dt. That means here we can write down the small a into rate of reaction. Similarly, rate of appearance B is equals to, see, rate of appearance of the B, here we can write down that rate of reaction with respect to B is equals to plus 1 by B d into concentration of B by dt. So, when the word reaction is used, we have to use the stoichiometric coefficients, or else rate of appearance of B, or else rate with respect to B is equals to plus d into concentration of B by dt. So, in the plus d into concentration of B by dt place, we can write down the rate of appearance of the B, and this small b, if you send that side, it becomes the rate of reaction. So that we can write down that rate with respect to B is equals to rate of reaction into small b, that is stoichiometric coefficient. Means for any particular reaction, if you want to get the rate with respect to any compound, then that value is equals to rate of reaction into its stoichiometric coefficient in the balanced equation. So here we can get the formula that rate with respect to any compound. So this may be rate of appearance or rate of disappearance is equals to rate of reaction into stoichiometry coefficient. So let us take some examples to understand this concept easily. Let us take an example. N2 reacts with 3 moles of hydrogen to give 2 moles of ammonia. So here rate of reaction is equals to minus d into concentration of N2 by dt is equals to minus 1 by 3 d into concentration of H2 by dt is equals to plus 1 by 2 d into concentration of NH3 by dt. So when you are using the word reaction means you are taking this relation. So you are relating the rate of every compound with each other in a reaction. That is what called the rate of reaction. There we need the stoichiometry coefficients. So now here rate of disappearance of nitrogen means rate with respect to only nitrogen I want. That means minus d into concentration of N2 by dt. And rate with respect to the hydrogen to be represented as minus d into concentration of H2 by dt. Rate with respect to ammonia is equals to plus d into concentration of NH3 by dt. When rate is used, we don't use the stoichiometry coefficients here. So this is only rate of reaction. So how to relate this rate and rate of reaction? Rate with respect to nitrogen is equals to rate of reaction into 1. Why? Because here only one stoichiometry coefficient is present. Rate with respect to the hydrogen is equals to rate of reaction into 3. Means the rate of hydrogen is 3 times of the rate of the reaction. Means whatever the speed of the reaction is going, in that hydrogen consumes 3 times faster than the other reactant molecules because 3 moles of reactant hydrogen is involved. For every 1 mole of the nitrogen, 3 moles of the hydrogen consumes in the reaction. Rate with respect to the ammonia NH3 is equals to rate of reaction into 2. So like this we can calculate the rate and the rate of reaction from the given balanced chemical equation. Calculation of rate with respect to mass per time. So that in this condition here is rate is equals to difference in the concentration divided by difference in the time. Concentration means number of moles per volume. Number of moles means weight by molecular weight. Now let us substitute this terminology there. So in the place of concentration I can write down the rate means difference in the mass divided by difference in the time into 1 by volume into molecular weight. Provided that volume is constant in a particular reaction, so that I can take this one as a difference in the mass of the reactant molecules or product molecules divided by difference in the time is equals to 1 by molecular weight of that particular compound. So now let us take a reaction. AA gives some BB is there. In this rate of reaction we can write down as minus 1 by A d into concentration of A by dt is equals to plus 1 by B d into concentration of B by dt. If you want to calculate rate of disappearance of A, minus d into concentration of A by dt is equals to plus A by B d into concentration of B by dt. This is the way we can calculate when concentrations are given. But when mass per time is given, in the place of concentration we have to use the word mass. Then it's molecular mass is there. This could be molecular mass. So then in this case, minus d into weight of A divided by time into 1 by molecular weight of A is equals to A by B into difference in the weight of B divided by dt into 1 by molecular weight of B. Then you send the molecular weight that side. So we get minus d into weight of A divided by dt is equals to plus A by B d into weight of B by dt into molecular weight of A divided by molecular weight of B. So this is the way to calculate the mass per time. Let us take a realistic example. 2SO2 plus O2 gives rise to SO3 is there. So in this reaction, in terms of the normal terminology, rate of reaction can be written as minus 1 by 2 d into concentration of SO2 by dt is equals to minus d into concentration of O2 by dt is equals to plus 1 by 2 d into concentration of SO3 by dt. But when the mass per time, when you are using the mass per time relation between these two, see here minus d into mass of SO2 changed per time is equals to 2 and 2 cancel out, so that here we will get the plus d into mass of SO3 changed per time into molecular weight of SO2 divided by molecular weight of SO3. Means its molecular weight we take in the numerator, this molecular weight we take in the denominator. So whenever the calculations are given per mass per time, we can use this formula to calculate that. During the decomposition of H2O2, the mass of H2O2 changed is 0.68 gram per hour. Then find the mass change for both H2O and O2. So this is the question. Let us try to solve this one. Solution. Let us write down the balanced equation for this. H2O2 decomposes to give H2O plus half O2. So if you write down the rate of reaction for this, so here rate of reaction is equals to minus d into concentration of H2O2 divided by dt is equals to plus d into concentration of H2O by dt is equals to plus 2 into d into concentration of O2 by dt. But here the question is asked about the mass per time. So the rate of change of the H2O to mass per time is given, so that we need to calculate both of these. So let us try to relate both H2O and H2O2 first. So finding the mass of H2O that is produced. So here the relation is minus d into mass of H2O2 divided by dt is equals to d into mass of H2O by dt. That we have to calculate this value, so that molecular masses we shall write down this side. So molecular mass of molecular weight of H2O divided by molecular weight of H2O2. So that mass change of the mass of H2O divided by dt is equals to change of the mass of H2O2 is given as 0.68 grams per hour into molecular mass of H2O 18 and molecular mass of H2O2 32 plus 34. So that by solving this we shall get it. And next one is relation with the H2O2 and O2 because they asked about O2 also. So second one is the relation between both of these is here minus D into concentration of H2O2 by dt is equals to plus 2 into D into concentration of O2 by dt. So this is in terms of the concentration. We shall change this one into the mass per time. So now I want the D into mass of O2 changes per time is equals to 2 comes this side. So this will become 1 by 2 into D into mass of H2O2 changed per time, mass of H2O2 decrease into molecular weight of this side molecule, that is oxygen, divided by molecular weight of H2O2. So now D into mass of oxygen, that is going to be changed, either means produced, into half of 0.68 into molecular mass of oxygen is 32, H2O2 is 34. By solving this, we shall get. So in this way, mass per time means mass of the compound change, either a product or a reactant changed per time when given. So the mass per time for the other components can be calculated using this type of the formula and calculations. Let us see one more question. The given reaction is N2O5 changes to NO2 plus half O2. Given that minus D into concentration of N2O5 by dt is equals to K1 into concentration of N2O5 plus D into concentration of NO2 by dt is equals to K2 into concentration of N2O5 plus D into concentration of O2 by dt is equals to K3 into concentration of N2O5. The data is given like this. Find the relation between K1, K2 and K3. So let's try to solve this question here. Solution. Write down that equation, balanced equation. N2O5 changes to NO2 plus half O2. So for this reaction, first of all, let us write down the rate of reaction. So rate of reaction is equals to minus D into concentration of N2O5 by dt is equals to plus 1 by 2 D into concentration of NO2 by dt is equals to plus 2 into D into concentration of O2 by dt. Now in these respective places, we have to substitute this data. Minus D into concentration of N2O by dt means K1 N2O5. So in this place I can write down K1 into concentration of N2O5 is equals to 1 by 2 into dNO2 by dt equals to K2 N2O5. So this I am going to write down the K2 into concentration of N2O5 is equals to 2 into dO2 by dt is equals to K3 N2O5. So I shall write down this one as K3 into concentration of N2O5. Basically concentration of N2O5 cancel out. So rest of the values are K1 is equals to K2 by 2 is equals to 2k3. This is one relation. If you don't want the relation in terms of the fractions, then multiply the entire equation with 2. The reason to multiply the entire equation with 2 is here denominator is 2, so that both get cancelled out. So it becomes now 2k1 is equals to k2 equals to 4k3. So we get the relation among these. So dear students, I hope you understand today's class. We shall meet in the next class. Thank you, one and all.